The second technique we are going to discuss is generalizing theorems. Generalizing a theorem. So for some statement, introducing a lemma doesn't work. Suppose that we'd like to prove a statement, and we usually start by applying rule induction. And perhaps we have several cases. And suppose that one of these cases requires its own inductive proof. So we have seen such a problem in the previous video. So in order to prove the final statement, we apply induction. But one of these cases requires its own inductive proof. Then, in order not to complicate the whole presentation, we take this guy as a separate lemma and then give a separate proof using induction, and then go back to simplify the presentation. But sometimes this idea of introducing lemma doesn't work because induction doesn't work. In that case, we want to generalize this statement so that a direct proof attempt by rule induction would work. So let's consider an example. Basically, the plan is, instead of proving this original statement, we'd like to generalize. So this is generalize. And we have another statement. This is something stronger than the original statement. It's stronger. So perhaps more challenging to prove. It's harder to prove, but more expressive than the original statement. So once you complete the proof of this generalized statement, you'd obtain the original statement right away as a corollary. That's the plan. So let's consider an example. We'd like to show that any string of matched parentheses is recognized by this judgment M parent. So in other words, if S is indeed a string of matched parentheses, then we can prove this judgment as M parent. First, we need to formalize the notion of being a string of matched parentheses because this statement is sort of informal. So remember that we are trying to prove that a given string is indeed matched, not just that the number of left parentheses is equal to the number of right parentheses. So for instance, if we have this one, then this is matched. But what about this one? This is clearly not matched. But still, the number of left parentheses is 1, and the number of left parentheses is 1, and the number of right parentheses is also 1. So we don't want to accept this sort of string. So first, we need to formalize the notion of a string being a string of matched parentheses. So we introduce a new judgment where we write K triangle S. And the idea here is that K copies of opening left parentheses. So we have K copies here, followed by string S is a string of matched parentheses. So it's matched. And where K denotes the number of left parentheses in the prefix, so K should be non-negative. So we introduce this new judgment. Let's develop a system of inference rules for this new judgment. First, what about epsilon? If that is, what if this string s is epsilon? Then there should be no left parentheses. So this guy requires 0. This is the p epsilon. Now suppose that we have k here, triangle, and we assume that the string starts with left parentheses. Then, according to the definition of this judgment, the intention is we have k copies of left parentheses. So we have k copies followed by left parentheses followed by s. So it's equivalent to saying that we have k plus 1 copies followed by s. So now the problem reduced to proving k plus 1 triangle s, this new judgment. Let's say this is the p left rule. So the best way to read this rule is from the conclusion to the premise. You want to read this rule bottom up instead of top down. And what about k triangle? This time the string starts with right parentheses. Then according to the intention, the definition here, this thing means we have k copies of left parentheses, and then we have this right parentheses followed by s. Then these two parentheses cancel each other. Now, once we cancel these two guys, then we are left with k minus 1 copies. So we can ignore these two guys. So the problem now reduced to k minus 1 triangle S. And we have to make sure that we have some left parentheses from the prefix. If we have no left parentheses, then this is not matched. For example, something like right parentheses. If the string starts with this right parentheses without no left parentheses in the prefix, then this is not matched. So we require that this k must be greater than 0. If this is 0, then it's not going to be accepted. So we have developed these 3 inference rules. Let's say this is a p right. The name of this inference rule is p right. We introduce new judgment, and we have these 3 inference rules. Now here's an example. Let's show that this string is matched. So in order to show that this string is matched, you start with 0 triangle the string. And first we apply this p left rule because it starts with this left parentheses. So this is going to be 1 triangle the remaining string. So this is a p left. And again, the first parenthesis is left. So we apply p left one more time. 2 triangle this string. Now it's time to apply this p right rule. But first we have to verify that the integer, the count of the opening left parentheses, is greater than 0. So we have to verify that 2 is greater than 0. So this is true. So now we decrement the count and then get rid of this one. So we have right parentheses. So this is an application of p right rule. Now let's apply this p-right rule one more time, because the first symbol is right parentheses. We have to verify that 1 is greater than 0 from this one, and then show that the count decrements to 0 and the remaining sequence is empty. And this is provable by applying p epsilon rule. So this derivation tree shows that this string is indeed matched. So now we have two judgments. This m-parent judgment, whose inference rules were given previously, and we introduced new judgment, this one, where we have these inference rules. Now I would like to prove this theorem. If string S is indeed matched according to the new judgment, then I'd like to show that this string is accepted or recognized by this judgment m-parent. So this is the this judgment states that string S is matched, and this judgment says this judgment m-parent accepts this string S. So we'd like to prove this. So let's apply rule induction and see why the proof gets stuck. The proof by rule induction on this judgment 0 triangle S. Let's consider this case. So we apply p left rule. So this is p left rule. So the string must start with the left parentheses. So in this case, we have left parentheses S prime. So where S is equal to left parentheses S prime. In that case, we want to prove the premise, which is 1 triangle S prime. Now we see why applying rule induction doesn't work for this theorem. The reason being that in order to apply rule induction or obtain an induction hypothesis, we'd like to say something like by induction hypothesis, this justification, we'd like to obtain some new fact. But the problem is the premise has different form from the judgment in the original statement. This statement requires the count to be 0, but we have a count 1. So we cannot even apply induction hypothesis. We cannot obtain induction hypothesis from the premise because this judgment looks different from this judgment. Because we cannot apply rule induction, it doesn't help to introduce lemma here. Remember that introducing lemma works best. We introduce lemma here when the subcase requires an inductive proof for itself. In that case, in order not to complicate the whole presentation, we'd like to extract this subcase as a separate lemma, give inductive proof, and then utilize it later. But here, we cannot even obtain an induction hypothesis from the premise because these two judgments have different forms. So in order to be able to apply rule induction, we have to generalize this statement so that the induction hypothesis can be obtained from the premise. So we have to generalize. So this is generalized statement. You may call it theorem, or you may call it lemma, or you may call it proposition. There's no particular rule saying which statement must be called a theorem or which statement must be called a proposition. But usually lemma is introduced as a statement that helps to prove something stronger. So we have to generalize this statement, this theorem. So let's call it the lemma. And in this particular case, you'd like it to generalize in this way. If K triangle S holds, then K copies of left parentheses followed by S, it is recognized by disarrangement and parent. This is what you want to prove. Then we see that rule induction works because, for example, if the last inference rule was a P left rule, then the premise would be K plus 1 S prime, where we have left parenthesis S prime. Because this statement allows an arbitrary count integer K, if K is greater than non-negative, we can obtain induction hypothesis from the premise. Now, thanks to the generalization of the statement here, now we can obtain induction hypothesis from the premise. So in this case, we can say by induction hypothesis, we have K plus 1 copies of left parentheses followed by S prime. This is accepted by M parent. And if you think about this, this is equal to K copies of left parentheses followed by S, because S is equal to left parentheses S prime. So the case is gone. Notice that we do not introduce a separate lemma. It's just a direct result of generalizing this statement into this something stronger. So this example illustrates when we needed to generalize a given statement, when introducing a new lemma doesn't help. And finally, I'd like to remark that this generalizing a theorem, this technique does not have a particular recipe. What that means is that for a problem that requires this generalization, you have to figure out some unique way of generalizing the statement specific to this problem, because there's no particular recipe. And sometimes this generalizing a given statement can be quite challenging. It could take many hours, many days, and even many months. And it requires a deep insight into the system of inference rules and the characteristics of the judgment. So you have to think carefully about how we should generalize the statement. In this particular example, the way that we generalize the statement is by relying on the intuition behind the whole judgment K triangle S.